In section 3.3, we look at polynomial division and then the remainder and factor theorems. First, let me give you the division algorithm for dividing polynomials. So let p of x be a polynomial divided by a non-zero polynomial d of x. Then there is a quotient polynomial q of x and a remainder polynomial r of x, such that p of x is equal to d of x times q of x plus r of x, or equivalently we can say p of x divided by d of x equals q of x plus r of x divided by d of x, where either r of x equals 0 or the degree of r of x is less than the degree of d of x. Okay, that is a lot to take in at one time. So rather than do an example with polynomials, I am going to do an example with simple numbers so that we can get an intuition for what we're talking about here. Suppose I give you the fraction 16 over 5. Let's remember that this means 16 divided by 5. And we know that we can actually perform this division by using long division. So we make our long division symbol, we put 16 on the inside and 5 on the outside. And remember again, so the 16 is what we call the dividend, 5 is what we call the divisor. So we have 16, the dividend, divided by the divisor 5. Now we know that 5 divides into 16 3 times, and that's because 3 times 5 is equal to 15, and then if we subtract, we get a remainder of 1. Now let's think about what that means. So when you first learn about division, you will learn that 16 divided by 5 is equal to 3 with a remainder of 1. This is one possible way to express the answer. But another way to express the answer is the number 16 is equal to the product of 3 and 5. So it's equal to 5 times 3, and then plus the remainder, which is 1. And you can see that this is true. 5 times 3 is 15, plus 1 is 16. And then the other way we can talk about division is when you divide 16 by 5, it goes in 3 whole times with 1 left over, and the 1 that is left over, if you divide that by 5, you would end up getting 3 1/5. So we have the very elementary way of expressing the answer where we just give the number of times that 5 goes into 16 and then how many are left over. We have an alternative way to express the answer, which is 16 is the product of 3 and 5, but then there's 1 left over, so when you add the leftovers, you get the whole thing there. And finally, 16 divided by 5 is an improper fraction. You can express it as a mixed number by using what we did here. So that is what we're talking about in this case here. Okay, so that one is this, and then this one here is this. And the way we know that is because when we write that second one, we can say 16 divided by 5 is 3 plus 1/5. It's just that when you have a couple of numbers, a whole number and a fraction, we don't put the plus sign in between it. We take it out, and we call that a mixed number. But what it really means is 3 plus 1/5. So that's what happened here. 16 divided by 5, that's your p of x divided by d of x, equals a quotient. How many times did it go in? It went in 3 times. Plus the remainder, what was the leftovers? Leftovers was 1. And you put that over your original divisor, which again is this 5 over here. So this is what we call the division algorithm. So we're going to be doing the same thing, but we're going to do it for polynomials. Now let's talk about factors and remainders. So it says here, let a polynomial p of x be divided by a non-zero polynomial d of x, and it has a quotient q of x, and a remainder polynomial r of x. If the remainder is 0, then we say that d of x and q of x are both factors of p of x. So to show you an example of this, again, let's take a very simple example. Suppose I asked you to do 15 divided by 5. You can do this using long division. 15 divided by 5. We know 5 goes into 15 3 times. And we know that 3 times 5 is 15, so when we subtract there, we get 0. So notice that we have a remainder of 0. Well, when your remainder is 0, that is special. What it means is that the number 15 is the product of those two numbers. So it means that 15 is equal to 5 times 3. So if the remainder is 0, it means that both your divisor and your quotient are factors of that number. Or, in the case of polynomials, they are both factors of that polynomial. Now we look at an example using polynomials. So in this first example, it says to determine the factors by division. So we want to divide to determine whether x minus 1 is a factor of the polynomial x squared minus 3x plus 2. So that means we're taking the polynomial x squared minus 3x plus 2, and we are dividing that by x minus 1. And so we can write it in fraction form like I have it there. You can also write it using the division symbol. If you do this, you need to make sure you put parentheses around both of these. That indicates that we are dividing this whole thing by this whole thing. But to actually do the division, we need to use long division. So we're taking x squared plus 3x plus 2, and we are dividing that by x minus 1. So the question is, how do you do the division when you don't have numbers? How does it work when you have variables? Well, the way it works is you focus on only the first two terms. So it's very important when you're doing this to have both polynomials in descending order. So the highest power of x needs to be here, and then the next highest power all the way down. Also outside here, the highest power of x is first, and then descending from there. So now when I'm doing this, I'm taking x squared and I'm dividing it by x. And we can do that division off to the side. X squared divided by x, we can do by subtracting the exponents, right? 2 minus 1 is 1, so x squared divided by x is just x. So I'll put that here. Now, just like we do with numbers, we are going to multiply x by the divisor. So after that, we are going to multiply x times x minus 1, and when you do that multiplication, you get x squared minus x. So when you multiply these here, you put the result down below. So it goes like this. X times x is x squared, and x times negative 1 is negative x. After that, you have to subtract. Now, this is the tricky part. When you just have numbers, it's relatively simple because you're just subtracting that number. But in the case where you have an entire polynomial down here, when you subtract this, you have to subtract both terms. So we're going to subtract the first term and the second term, and when you subtract the second term, it changes the signs. From there, we add these together. X squared plus negative x squared is 0. Negative 3x plus 2x, negative 3x plus 1x is negative 2x. And then this positive 2 we will bring down for the next step. From here, we just repeat the process. So now we're focused on the very first term of what we have left, which is negative 2x. And that negative 2x gets divided by the divisor here, which is x. So again, you're just focusing on those first two terms. Well, what is negative 2x divided by x? Well, it is negative 2. and that is what goes up here. And then from there, we're going to multiply like we did before. So we're going to multiply negative 2 times x minus 1. And this is negative 2x plus 1. So when I multiply negative 2 times x, we get negative 2x. And negative 2 times negative 1 is positive 2. Now when I get the positive 2, I'm just going to write 2. I'm not actually going to put the positive sign. Okay? I'm just going to put 2, and the reason for that is because after we do that, we have to subtract, right? And when you subtract these, you change the signs. So this becomes a positive, and this becomes a negative. And now notice when you add these together, you get 0. So what does that mean? Well, the remainder equals 0. If the remainder is 0, it means that both of these are factors of the original polynomial, this thing. So what it means is x squared minus 3x plus 2 is equal to x minus 1 times x minus 2. So it says divide to determine whether x minus 1 is a factor of that polynomial. The answer is yes. X minus 1 is a factor of that original polynomial, x squared minus 3x plus 2. And again, it's because the remainder was 0. In our next question, it says to find the quotient and remainder when this polynomial here, too long to say, is divided by 2x plus 3. So once again, to do this, we need to set up a long division problem. So here is the division that we are attempting to do. And to do this division, we'll go ahead and put this in long division format. And then the process is the same as what we did just a minute ago. You only focus on the leading term here and the leading term here. So for this first step, we are looking at 2x to the fourth divided by 2x. And this is x to the third power. Again, you're just subtracting the exponents. And of course, the 2's there cancel out. So when you divide those, you get x cubed. After you get the quotient there, you're going to multiply that quotient to the divisor. So x cubed times 2x is 2x to the fourth. And x cubed times 3 is positive 3x cubed. Now, when I get a positive, I don't put the plus sign here. Okay, and I'll explain why in just a second. Let me put the plus sign and I'll show you why I don't do this. The next step is you have to take the opposite of what you have here. So when you take the opposite here, it's clean. But when you take the opposite here, you have to put a negative in there. So this is why I don't like putting the plus sign there. So when I multiply x cubed times 3, I get positive 3x cubed. I leave it blank. And then when I go into subtract, I get a nice, clean negative sign. Now we combine like terms. 2x to the fourth, take away 2x to the fourth, cancels. 7x to the third, take away 3x to the third, is positive 4x to the third. And then the rest of these we will bring down for the next step. And we're bringing those down because there is nothing added or subtracted to those. Then we repeat the process. We focus on the first term here and the first term here. So we take 4x cubed divided by 2x. 4 divided by 2 is 2. X cubed divided by x is x squared. So when we divide 4x cubed by 2x, we get positive 2x squared, and that goes here. And then we do the same thing. We take that part of the answer, just this part, not the whole thing. 2x squared gets multiplied to 2x plus 3. 2x squared times 2x is 4x to the third. And 2x squared times positive 3 is positive 6x squared. And then we have to change the signs. We get that from subtracting. Notice once again, the first terms cancel out. That always happens, by the way, if you do it correctly. Then 4x squared take away 6x squared is negative 2x squared. And then these can be brought down. And we keep going. And then we will proceed with the next step, which is to take the leading term here and the leading term here and divide those. So we have negative 2x squared divided by 2x. This is equal to negative x, and that is what goes here. And then we multiply once again. So hopefully you're getting the hang of it because it's the same process each time. So now we take this algebraic term, negative x, and we multiply it to 2x plus 3. So negative x times 2x is negative 2x squared. And negative x times positive 3 is negative 3x. And then don't forget you have to subtract, which is going to change both of those signs. From there we get cancellation here. And negative 7x plus 3x is negative 4x. And the minus 6 will come down, and we're almost done. Now, by the way, we know we're not done yet because the power here is x to the 1, and the power of what you are dividing by is also x to the 1. So you stop when your remainder has a power that is less than the divisor. So right now they're the same power, so we keep going. So we take negative 4x and divide it by 2x. And this is equal to negative 2. That goes here. And then we multiply. Negative 2 times 2x is negative 4x. And negative 2 times positive 3 is negative 6. And don't forget, you have to subtract those, which means change the signs. And notice in the end, once again, we get a remainder of 0. So now, first of all, this remainder is not always going to be 0. So that's special, okay? But it happens to be 0 in this case. So now it says, find the quotient and the remainder. Well, the quotient is the main part of the answer. So this part is called the quotient. And the part down here, as I just mentioned, this is the remainder. And so the quotient is, this here, and the remainder is this here. Now, again, what does that mean? The fact that the remainder is 0 is special, and it means the original polynomial is equal to the product of the divisor and the quotient. All right, and so that's what that means. And there's no remainder on the end. So if this remainder had been, a number besides 0, we could add that on to the end here. But since the remainder is 0, this is it. So what it means is that our original divisor is a factor of this polynomial. And also our answer, our quotient, is a factor of that polynomial. So let's go ahead and do one more example here. In this problem, we have the polynomial p of x is 6x cubed plus x minus 1, and we are dividing it by x plus 2. So we need to set up a long division problem. I always like to start with the fraction. So we're taking this polynomial and dividing it by this polynomial. And to do this, we will set up our long division. Now, when you set up your long division, I want you to notice that the dividend is missing the x squared term. So we should account for that by leaving a blank here before we put the plus x and the minus 1. Now you'll see why we should do this in just a minute. If it bothers you to put a blank, then what you can do is you can write plus 0x squared there as a space filler to help you set this up correctly, okay? But let's go ahead and go through the long division process. So again, you focus on the first term here and the first term here. So 6x cubed divided by x. This is going to be 6x squared. And then we multiply 6x squared times x and 6x squared times 2. And when we do those multiplications, we get 6x cubed and 12x squared. And then don't forget we have to subtract these. Now, this is why you want to have the 0x squared here, because notice now we have like terms that are lined up. If this x had been here, then you would have lined up unlike terms, and it makes it a little bit harder to see what is happening. But in this case, we know that these cancel out, and 0x squared take away 12x squared is negative 12x squared. And then we repeat the process. Take negative 12x squared and divide it by x. And this gives us negative 12x. And that goes here. And then we take negative 12x, multiply it by x, which gives us negative 12x squared. And negative 12x times 2 is negative 24x. And then we subtract, which means we change the signs. Combine like terms, these cancel out. 1x plus 24x is 25x minus 1. And we have one more division to do here. First term here is 25x. Divide that by the first term here, which is x, and that gives us positive 25. And then we multiply. 25 times x is 25x. And 25 times 2 is positive 50, so I'll just write 50. And then we have to subtract those. And we get negative 1 minus 50 is negative 51. So again, this is our quotient. That's the main part of our answer. And this negative 51 is our remainder. Now, what does that mean? Well, it means that when you write your answer, it's going to be a little bit messier because your remainder is not 0. So x plus 2 is not a factor of the original polynomial, and neither is the quotient. So these are not factors of that polynomial. So how do you write your answer? Well, they tell us that they want us to write the answer in this way. So we're going to say the original polynomial, 6x cubed plus x minus 1, divided by x plus 2, is equal to the quotient, which is the main part of the answer here, 6x squared minus 12x plus 25, plus, and then you take the remainder, which is r of x, which in this case is just negative 51, divided by the divisor, which was x plus 2. So that's how they want you to express the answer here. Now, one little thing to point out in the answer, and that is that when you have addition and then a negative, you could just change this to subtraction. So you could also write the answer like this. So either one of these is fine, but this is a little bit cleaner, right? Because we don't have plus and then a negative. We could just say minus instead. Now let's talk about synthetic division. This is a game changer. When dividing certain types of polynomials, you can use a process called synthetic division. It is a much simpler process than long division. Now, when can you use synthetic division? Synthetic division can be used when your divisor has the form x plus the number c or x minus the number c. So in other words, you are dividing by a linear polynomial, so x to the first power, and the coefficient of x has to be 1, and then you can have a positive number here or a negative number there. So this case is a case where you can use synthetic division because the divisor here is x plus 2. So how does the process work? Well, what we're going to do is we're going to form a little half box here. And inside of that box, we are going to take the opposite of the number in the divisor. So the opposite of positive 2 there is negative 2. We are then going to list the coefficients of the main polynomial, the dividend, the thing that we are dividing. So the dividend, in this case, is 6x cubed plus 0x squared plus 1x minus 1. So this is this polynomial. It is absolutely paramount that when you are talking about your dividend, you must put the missing powers of x. So what we're going to do now is we're going to take those coefficients, these numbers, and we're going to write them down here in a line. So first we put 6, and then 0, and then 1, and then negative 1. Okay, so this is the setup for synthetic division. Now, how does the process work? What you're going to do is you're going to take this leading coefficient of your dividend, and we're going to bring that down, and we're going to draw a line and put it below that line. Okay? So now we are ready to actually go through the synthetic division process. Now, the way this works is very simple. You're going to take the number in the box, and you're going to multiply it by this number here. So negative 2 multiplied to 6 is negative 12. And then these two numbers you are going to add. 0 plus negative 12 is negative 12. And then you repeat that process. We take the number in the box, negative 2, and we multiply it by the number here, negative 12. Negative 2 multiplied by negative 12 is positive 24. And then we add these numbers. 1 plus 24 is 25. And then we do it one more time. We take the number in the box, negative 2, multiplied by the number here, 25. Negative 2 times 25 is negative 50. And then we add these numbers together. And when you add those numbers together, you get negative 51. Well, the negative 51, this last number, of course, is your remainder. And the nice thing is, these are the coefficients of your quotient. So what is your answer then? Well, originally, you had a third-degree polynomial, and you were dividing it by a first-degree polynomial. So in your answer, it's going to be, the power is going to be 1 less than the power that you started with. So instead of having a third degree, down here we're going to have a second degree. So the 6 is the coefficient of x squared. So we have 6x squared. The negative 12 is the coefficient of x, so it's negative 12x. The 25 is your constant term, so that's positive 25. And then we have plus the remainder, which is negative 51, and you have to know that your remainder goes over your original divisor, which was x plus 2. This is your answer. Now, if you compare that with the answer that we got on the previous page, you'll find that they're the same thing. So just for reference, here are the answers that we got on the previous page, right? So, same answer. But this process is super clean and very efficient. And when you get used to it, it's also really simple. Let's do another example before we move on, just to make sure we understand the synthetic division process. So here we have the polynomial 5x to the fourth plus x cubed minus 3x plus 2, and we're dividing it by x minus 1. So the synthetic division process says, first of all, make a box, and we're going to take the opposite of this number, So the opposite of -1 is +1, and we put that number in the box. Then we are going to take all the coefficients that we have here. So this is a 1. And keep in mind that we have a 0x squared there. And we're going to write down those coefficients in order. So 5x to the 4th, 1x to the 3rd, 0x to the 2, -3x to the 1, and +2. And then that 5 we always bring down below the line. Okay, so that's the setup. And now the synthetic division process. We multiply 1 times 5. 1 times 5 is 5. And then we add 1 plus 5 here is 6. Repeat. 1 times 6 is 6. Add these numbers. 0 plus 6 is 6. Repeat it again. 1 times 6 is 6. -3 plus 6 is +3. And finally, 1 times 3 is 3. And 2 plus 3 is 5. See how fast that is? This is our remainder, and this represents our quotient. So what is our answer going to be? Well, again, you had a 4th degree, and you divided it by a 1st degree. So our answer is going to be a 3rd degree. When you use synthetic division, your answer is 1 degree less than the degree you start with here. So this 5 represents 5x to the 3rd. This 6 represents +6x squared. The next 6 represents +6x. And then +3. So that's our quotient, right? That's the main part of our answer. But then we have to add the remainder, which is 5, and that remainder goes over the original divisor, which was x minus 1. So again, here are all the parts. Okay, so you have the quotient, that's the main part of the answer, plus the remainder, that's this last little piece, and it goes over the divisor. Divisor means the original thing that you were dividing by. So the synthetic division process is awesome. Now let's take a look at a very interesting theorem. This is called the remainder theorem. And it says that when you have a polynomial p of x and you divide it by x minus c, the remainder is equal to the value of p of c. So the remainder when you divide it by x minus c is equal to the value of plugging c into the function. So what this is telling you is that if you have a polynomial p and you want to plug the number c into that polynomial, all you have to do is divide by x minus c and look at the remainder when you do that division. So the reason the remainder theorem is useful is because it allows you to use synthetic division to find function values of polynomials. So let's take a look at this example here. Here it says p of x is this polynomial, and we want to use synthetic division to evaluate p of 2. So when I want to use the remainder theorem to evaluate the function value of 2, I put 2 in the box. So notice that I don't have to take the opposite of it. That's because it says in the theorem that to find p of c, that's the same as looking at the remainder when you divide by x minus c. And you remember, you always take the opposite of whatever this number is. Well, the opposite of negative c is c. So when you're trying to find a function value, it's really cool. You just put that value in the box. Then we have to get all the coefficients. So we have -2 x to the 4th. We have +6 x cubed. Notice that we have 0x squared once again. Then we have 3x. And finally, we have -1. The -2 here comes down below the line. And now we start the synthetic division process. So we'll go through it again. So we multiply 2 times negative 2, which is negative 4. And then we add 6 and negative 4 is positive 2. And then we multiply 2 times 2 is 4. And then we add these together and we get 4. And 2 times 4 is 8. And we add 3 and 8 to get 11. And finally, 2 times 11 is 22. And when you add negative 1 plus 22, you get 21. So, using synthetic division, we can see that P of 2 is equal to 21. Now, does it really work? Well, let's check it. How would you do P of 2 the old-fashioned way? Well, you would just plug it into the function, right? I mean, you know P of x is this polynomial. So if I plug the number 2 into that polynomial, I'm going to put 2 in for x in all those spots. So if I do that, I'm going to get negative 2 times 2 to the 4th power plus 6 times 2 to the 3rd power plus 3 times 2 minus 1. If you do the math on this, this is going to be negative 2 times 16 plus 6 times 8 plus 6 minus 1. That's negative 32 plus 48 plus 6 minus 1. And negative 32 plus 48 is 16. And 6 minus 1 is 5. And 16 plus 5 is 21. So I want you to notice that it's the same as the remainder when we use synthetic division. Now, I'm not saying that this is particularly difficult. It really isn't. But when you get used to synthetic division, I believe that you will find this process to be much easier than doing this. So this is just another way that we can use synthetic division. Pretty awesome. The final theorem for this section is the factor theorem, and it simply says the term x minus c is a factor of the polynomial p of x if and only if p of c is equal to 0. Well, this should make sense because we already know that a polynomial is a factor only when the remainder is equal to 0. And the remainder theorem tells us that the remainder is the same as P of C. So if P of C is equal to 0, this means the remainder is 0. Right? And if the remainder is 0, it means you have a factor. So here's an example. Determine whether x plus 3 is a factor of this polynomial, 2x cubed plus 3x minus 2. So to do this, we'll set up a synthetic division problem. We're going to take the opposite of positive 3 there, which is negative 3. We're going to write down the coefficients of the main polynomial, which is 2x cubed. Once again, x squared is missing, so we need a 0x squared, a positive 3, and a negative 2. We're going to bring the 2 down below the line, and then we proceed with the process. Multiply here, add here, multiply these two, add, multiply, negative 3 times 21 is negative 63, and finally add these two numbers together, and we get negative 65. So the remainder here is not 0. So the answer is no. X plus 3 is not a factor of 2x cubed plus 3x minus 2. Because when we divided by x plus 3, we did not get a remainder of 0.